Alex, people think the heart of a workshop is the blade or the bit, but it's actually the pulse of the electricity hidden in the wall. Most folks just plug a tool in and pray the motor doesn't grumble. But when you step up to three-phase power or try to make a vintage lathe dance to a modern beat, you're basically trying to teach an old dog to do ballet.
And knowing you, that ballet usually ends with a blown fuse and you sitting in the dark, questioning your life choices.
More than once. I remember the first time I tried to wire up a 5 horsepower compressor without a soft starter. I hit the switch, and the lights in the entire neighborhood dimmed so hard, I thought I'd accidentally triggered an EMP. My neighbor's garage door actually started opening on its own. It's like the motor was sucking the soul out of the grid just to get those pistons moving.
That's the across the line start, right? Just dumping the whole bucket of juice on the motor at once?
Exactly, it's like trying to start a marathon by getting shot out of a cannon. It's violent. But that's why we're diving into variable frequency drives today. The VFD is the maestro of the shop. It takes that raw, angry AC power and turns it into something sculptural.
Okay, but for those of us who didn't grow up hugging transformers, let's peel the onion. A VFD, or an inverter, or a variable speed drive, whatever the manual feels like calling it today. What is it actually doing between the outlet and my motor?
Think of it as a 3-stage refinery. First, you've got the rectifier. It takes that AC power, which is constantly flip-flopping back and forth like a politician, and forces it to move in one straight line. It turns it into DC.
So it's like a gate that only lets traffic go one way.
Precisely. But that DC is messy, like a dirt road after a rainstorm. So it goes to stage 2, the DC bus or the DC link. This is the waiting room filled with capacitors that smooth out all those bumps and ripples until you've got a steady, flat pool of power.
The calm before the storm.
You're not wrong, because the third stage is the inverter. This is where the real magic and the expensive electronics live. It uses these things called IGBTs, which are basically light switches that can flip on and off thousands of times a second. They chop that flat DC back into a custom-made AC wave. By changing how fast and how long those switches stay open, the VFD can tell the motor exactly how fast to rotate.
So instead of the motor being a slave to the 60 hertz coming out of the wall, the VFD is basically hallucinating a new reality for it.
That's a beautiful way to put it. It's pulse width modulation. If I want the motor to crawl at a snail's pace so I can thread some steel without ending up in the emergency room, the VFD just narrows those pulses. The motor thinks it's getting a low frequency signal, so it behaves.
Wait, I've seen those VFD versus PLC debates online. Some people treat them like they're the same thing.
Oh, that's a classic shop floor misunderstanding. A PLC, a programmable logic controller, is the brain. It makes decisions like, if the sensor sees a box, move the belt. But the PLC is a weakling. It can't actually move the motor. The VFD is the muscles. The brain tells the muscle what to do, and the muscle handles the heavy lifting.
So if I'm building a project, why wouldn't I just use a mechanical variable speed? Like the pulleys on an old Bridgeport mill?
Man, I've spent half my life fighting with greasy belts and sticking step pulleys. Mechanical speed control is like trying to change gears on a bike while standing on the pedals. It's clunky, it wears out, and you lose torque. With a VFD, you get constant torque. You can slow that motor down to a crawl, and it'll still have the grit to chew through a piece of kiln-dried white oak without stalling out. Plus, it's a massive energy saver.
I read that industrial systems consume over 50% of the world's electricity, and VFDs could chop 10% off of global consumption? That's not just shop talk. That's save the planet talk.
It's the throttling that kills us. Imagine driving your truck with the gas pedal floored, but you control your speed entirely by riding the brakes. That's what a motor running full tilt against a mechanical valve is doing. A VFD just lets the motor breathe. It only drinks as much current as it needs to do the job.
Okay, Tiger, let's get into the weeds. If I'm standing in the tool graveyard, also known as your back shed, and I find a motor I want to hook up, how do I pick the right drive? I've seen micro, general purpose, and high performance.
Choosing a VFD is like buying a pair of boots. You don't buy stilettos to go logging. First, you look at your full load amperage, the FLA on the motor's nameplate. Never size a drive by horsepower alone. That's a rookie move that leads to the magic smoke leaving the electronics. You need a drive that can handle the actual current that motor's going to suck down when it's under a real load.
And what about the inverter duty motors? I see that label everywhere. Can I not just use any old 3-phase motor I found at the scrapyard?
You can But you're playing a game of chicken with the insulation. See those high-speed pulses from the VFD? They create these tiny voltage spikes. Over time, those spikes act like 1,000 little hammers hitting the wire insulation inside the motor. An inverter-duty motor has extra thick armor on its windings to handle that abuse. If you use a standard motor, just don't be surprised if it eventually develops a fever and quits on you.
Speaking of fever, let's talk about the disasters. You mentioned the neighbor's garage door, but what's the most common I definitely didn't read the manual mistake you see?
Heat and tight spaces. Folks love to tuck these drives away in a hidden corner or a sealed wooden box to keep the dust off. But a VFD is basically a space heater that happens to control motors. If it can't breathe, the capacitors will cook themselves. I once saw a guy build a beautiful airtight mahogany cabinet for his lathe's VFD. 2 hours into a turning session, the wood actually started to caramelize from the heat trapped inside.
Slow-cooked mahogany, very artisanal.
It smelled like a campfire in a high-end furniture store. The other big one is dynamic braking. If you have a huge, heavy grinding wheel spinning at 3,000 RPM and you tell the VFD to stop it in 2 seconds, all that energy has to go somewhere. The motor becomes a generator and pushes all that electricity back into the drive.
And the drive just explodes?
Not quite, but it'll trip an overvoltage error and leave your wheel spinning freely like a runaway freight train. You need a braking resistor, basically a toaster element that sits on top of the drive to burn that excess energy off as heat. Without it, you're just asking the VFD to catch a bowling ball with a paper plate.
Okay, let's talk about the weird stuff. Volts per hertz and sensorless vector control. Whenever I see those settings, my brain just defaults to factory settings and I hope for the best.
Don't be scared of the math. Volts per hertz is the basic setting. It keeps a steady ratio. It's like a steady diet for your motor. It works for most fans and pumps. But sensorless vector control, that's the high performance stuff.
Sounds like a sci-fi movie title.
It feels like it. The drive actually monitors the electrical echoes coming back from the motor. It calculates the exact position of the magnetic field in the rotor without needing a separate sensor. This gives you incredible control at very low speeds. If you're doing precision metal work, where you need that spindle to turn as slow as a clock hand, but still have enough torque to drill a 1-inch hole, vector control is your best friend.
What about the washdown NEMA 4X models? Is that for people who like to power wash their workshops?
Or for when the roof leaks. Actually, it's for food processing or really nasty environments. If you're in a shop full of conductive metal dust or fine flour, you want a NEMA 4X. It's sealed tighter than a submarine. A standard microdrive has cooling vents that act like a vacuum cleaner for every bit of metal filing and sawdust in the air.
Which is a great way to start a very expensive fire.
Precisely. You've got to match the enclosure to the environment. I've seen guys put an open frame drive right next to a grinding station. It's not a question of if it's going to go bang, it's how many seconds it'll take.
So, say I've got my FLA figured out, I've got the right enclosure, and I've warded off the heat demons. How do I actually talk to this thing? I see these keypads with 50 buttons and some have Modbus or Ethernet. Is my lathe going to start joining Zoom calls?
Well, not unless it wants to complain about the work-life balance. Most of us just use hardwired ISR-O. You wire a physical switch or a potentiometer, a little speed knob, to the terminals on the drive. It's tactile, it's reliable, and you can hit the e-stop without navigating a menu. But if you're running a big CNC or a multi-motor conveyor, Modbus, or Ethernet/IP, lets one computer tell 10 different drives exactly what to do simultaneously. It's like a conductor leading an orchestra instead of yelling at each musician individually.
I love that. But I've got to ask, PID tuning. Every time I hear that, it sounds like some kind of dark art performed by people who are way better at calculus than I am.
PID, proportional integral derivative. It sounds like a migraine, but think of it like this. Imagine you're trying to keep a car exactly at 60 miles per hour while going up and down hills. The P sees you're slow and hits the gas. The I remembers you've been slow for a while and gives it an extra nudge. The D sees you're accelerating too fast toward the target and starts to let off the gas so you don't overshoot.
That actually makes sense. It's just a feedback loop to keep things steady regardless of the load.
You got it. If you're running a pump and somebody opens another valve, the pressure drops. The PID loop tells the VFD to kick the motor into high gear to compensate. If you tune it wrong, though, the motor will hunt. It'll speed up and slow down in this nauseating cycle like a toddler on a sugar rush.
Tiger, we've covered a lot of ground today. From the internal rectify smooth invert process to the dangers of mahogany-flavored smoke. If some maker is sitting in their garage right now looking at a motor and a VFD, what's the one thing they should keep in their pocket?
Respect the ghost in the machine. A VFD is a powerful tool, but it's also sensitive. Don't just treat it like a dumb switch. Take the time to actually enter your motor's data into the parameters. Tell the drive who the motor is, how many poles it has, its base frequency, its full load current. If you befriend the drive, it'll protect your motor better than any fuse ever could. It'll watch for ground faults, it'll monitor the temperature, and it'll make your tools run smoother than they ever did on straight wall power.
So the takeaway is, don't just plug and play, plug and program.
Exactly. The manual might be translated poorly and have a font size that requires a microscope, but the secrets to a long, spark-free life are in those pages. And for heaven's sake, keep it cool. A happy VFD is a cold VFD.
Well, I think my brain has reached its FLA for today.
Fair enough. Next time, maybe we'll talk about how to actually wire one of these up without turning your workshop into a lightning storm. But for now, just remember, control the pulse and you control the machine.